here we're going to consider a type of transformation of a function that's called a translation. The idea is that we take the graph of some original function and then we obtain a new function by shifting this graph either vertically or horizontally without changing its shape. Let's first consider the case where we're shifting the graph either up or down, which is called a vertical translation. This is represented algebraically by adding or subtracting a positive constant c to the function. To see this, let's take some function f of x as shown in red here. And let's consider the graph of a new function defined by f of x plus c. So let's call our new function g of x, and g of x is equal to f of x plus c. What this means is that the output value of g is equal to the output value of f plus some positive constant c. In other words, for any particular input value x, the output of the function g is simply c units larger than the output of the function f. So the graph of g is simply the graph of f shifted upward by a distance c units. So, for example, it would look something like this, where this distance here is c for all values of x. In a similar way, if we define a new function g of x is equal to f of x minus some positive constant c, then the graph of this function g will be the same as the graph of f, but shifted downwards everywhere by c units. So in other words, it would look something like this, where again this distance here is always equal to c for all values of x. So this is g of x is equal to f of x plus c, and this is g of x is equal to f of x minus c, where c is a positive constant. Now let's consider horizontal translations, and horizontal translations are perhaps a little bit trickier than vertical translations. As we're going to see, a horizontal translation corresponds algebraically to adding or subtracting a positive constant to the input value of a function. So, for example, let's take our function f of x again as shown in red here, and let's consider graphing a new function called g of x, where g of x is defined to be f evaluated at x plus c. What does the graph of g of x look like? Well, the value of g at any particular input value x is equal to the value of the function f when evaluated at x plus c. For example, let's take an input value of 5. The value of the function g at x equals 5 is equal to the value of the function f at 5 plus c. Well, the value of f evaluated at 5 plus c we can find from the graph. Since c is a positive constant, 5 plus c will lie somewhere on the horizontal axis, and we can identify this vertical distance here as the value of the function f evaluated at 5 plus c. And so the graph of g is going to attain this height, but at an x value of 5. In other words, the graph of g is going to go through this point here. That point has an x-coordinate of 5 and a y-coordinate of f evaluated at 5 plus c. Let's take another point, for example, x equals 10. What is the value of the function g when evaluated at this point, x equals 10? Well, of course, from our definition, the function g at x equals 10 is equal to the value of the function f evaluated at 10 plus c. And again, we can locate 10 plus c on the horizontal axis here and recognize that this vertical distance here is equal to f evaluated at 10 plus c. So the graph of the function g is going to attain this height, but for an x value of 10. In other words, the graph of g is going to go through this point here, because that point has an x-coordinate of 10 and a y-coordinate of f evaluated at 10 plus c. In both of these cases, what you can see is that points on the graph of f of x get shifted to the left by a distance c units. And we could do this for any input value of x, and what we would see is all of these points get shifted by the same distance to the left, and so the graph of g is going to be a copy of the graph of f, but it's going to be translated to the left by a distance c. In other words, this distance here is c, this distance here is c, for all values of x. Now this is perhaps a little bit surprising. In the previous example, when we added a constant c to the function, that shifted our graph upwards. And you might initially expect that if we were to add a constant to the input value of a function, then that's going to shift the function to the right. But as we see in this example, horizontal translations don't work that way. The direction of shift in a horizontal translation is perhaps opposite to what you might initially expect it to be. In a similar way, we can consider what happens to our new function if it's defined as g of x is equal to f evaluated at x minus c. And it's not hard to convince yourself that if you go through an analogous argument, a very similar sort of thing will happen, but now the graph of f gets shifted to the right instead of the left.